This video follows up on the video Mechanics 1. If you have not yet seen Mechanics 1, then go and watch it right now. We left the link in the description below. Now without further ado, let's get into the video.
A matter of physics.
Hello everyone and welcome to the second video on mechanics. Today we're going to be looking at some pretty cool stuff. Newton's first three laws and a few different types of forces. Let's get straight into it. So, Newton's laws. Newton's first law states that if there is no force acting on an object, it's either at rest or moves with a constant velocity. For example, when a rocket is traveling in space and turns off its engine, it continues at a constant velocity because there is no force acting on it. Newton's second law states that the acceleration of an object as produced by a net force is directly proportional to the magnitude of the net force and in the same direction as the net force, and inversely proportional to the mass of the object. This basically means the higher the acceleration, the higher the net force. And if the acceleration is constant, the lower the mass, the higher the net force. For example, if the same amount of acceleration is acting on a car weighing 1 ton and a truck weighing 2 tons, the car will have a lower net force acting on it than the truck. If you don't know what net force is, don't worry, it will be explained later on in the video. Newton's third law states that for every action there is an equal and opposite reaction. Maybe you've heard of it as action equals reaction, meaning that if an object A exerts a force on object B, then object B must exert a force of equal magnitude and opposite direction back on object A. This tells us that forces always occur in pairs. For example, if a man jumps off the front of a small boat, then the boat will move in the opposite direction with the same force as the man jumping off. And that's Newton's third law. Now let's move on to forces. Here we have Mr. Sylvan skiing down the Matterhorn, and he's really enjoying it. But what forces are acting on Mr. Sylvan so that he can ski? First of all, the gravitational force. The gravitational force is the force that pulls Mr. Sylvan down towards the Earth, which means to find the gravitational force acting on Mr. Sylvan, we must calculate using the formula Fg equals ma, where m is Mr. Sylvan's mass and a is the acceleration, which in this case is gravitational acceleration, and can be written as a small g. So there we would have the gravitational force. But to understand the forces working on Mr. Sylvan better, we can decompose the gravitational force vector into two, Fg parallel and Fg perpendicular, where Fg parallel is called the downhill force and is parallel to the ground, and is important because in the absence of friction, Fg parallel is equal to the net force. And Fg perpendicular is obviously perpendicular to the ground, and is important because it is the opposite of the normal force. And the normal force is the force exerted by the ground. So Fg perpendicular is equal to negative Fn, where Fn is the normal force. This helps us a lot because when you bring friction into the picture, the stronger the normal force, the more friction there is. Which brings us to our next force, the frictional force. The frictional force results from two surfaces being pressed together closely. In this case, it is between the skis and the snow. The skis are being pressed into the snow by Fg perpendicular, and the snow, or ground, is represented by the normal force, Fn. Meaning that Fn and Fg perpendicular have a direct effect on friction. There are at least two types of friction forces, kinetic and static friction. In this case, we have kinetic friction because Mr. Sylvan is in motion, meaning we label the vector Fk. Lastly, we have the net force, which we find using the formula Fnet equals Fg parallel minus Fk. You can tell if the net force is correct because it should represent in which direction Mr. Sylvan is traveling. Now to complete our scenario, we can include air resistance, which is represented by F drag. Air resistance is an interesting kind of friction because it is affected by velocity. meaning that the higher the velocity, the higher the friction. This is why skydivers reach a constant velocity, and why they cannot eternally accelerate. To find air resistance, we must use this formula. Yeah, I know, it's pretty complicated. This symbol, the Greek letter rho, represents the density of the air. The capital A is the area of the object, and CD is a number representing the shape of the object, and V is velocity. If you think about this formula, it makes sense because all these variables would have an effect on Mr. Sylvan. And now our scenario is truly complete, and Mr. Sylvan can ski on home. So lastly, we would like to quickly mention another force that exists. This is the spring force. The spring force is the force exerted by a compressed or stretched spring upon any object that is attached to it. This links to Newton's third law, because if you want to compress or stretch a spring, you need to exert the same force on the spring. An object that compresses or stretches a spring is always acted upon by a force that restores the object to its rest or equilibrium position. For most springs, the magnitude of the force is directly proportional to the amount of stretch or compression of the spring. This is shown by Fs equals Kx, where K is the spring constant and X is the distance. This is called Hooke's law. That's it for this video, guys. Thank you for tuning in. We hope this video helps a lot and that you get a lot better grades than any of us. If you enjoyed the video, please smash that like button, and if you didn't, smash it anyway, and leave a comment below, and don't forget to subscribe. Peace.